In this video, I'm going to walk you through the topic of bond polarity and IMFs. All right, so we've been talking about covalent bonds here, the sharing of electrons, and we've just been assuming that the atoms were all sharing equally and everything was great. Well, that's not really what takes place in real life. All right, so these electrons here are actually in this what we call tug of war here between the two atoms. So the two atoms of the covalent bond are sharing these electrons, and each of them are pulling the electrons. All right, and sometimes somebody wins that tug of war. All right, and that's polarity. All right, so you kind of just want to imagine, like if you look here at this bond between the hydrogen and the fluorine, these electrons are being pulled toward the fluorine and they're being pulled toward the hydrogen. But in the case of fluorine, because of electronegativity here, the element's ability to attract electrons, fluorine is very electronegative, as you know. He actually pulls the electrons toward himself more frequently or holds them closer to himself more than the hydrogen. All right, so this is going to lead to this idea of bond polarity here. So again, you just want to imagine this tug of war taking place between the nuclei of the two different atoms, the electrons, the shared pair in between, and they're being pulled between the two atoms. And sometimes somebody wins that tug of war. If a covalent bond is considered to be nonpolar, that means there is an equal sharing of electrons. Okay, it is not polar, so therefore it is equal. All right, everybody shares equally. Some properties here of nonpolar covalent bonds. They are not soluble in water. There's this old saying, like dissolves like. Okay, so water is a polar substance. So polar substances typically dissolve in water. So non-polar substances do not dissolve in water. All right, and they have a little bit lower boiling and melting points than polar compounds. Remember, these are still covalent. They're going to have low boiling and melting points. It's just that these guys are a little bit lower than polar. All right. The easiest example I can give you of a non-polar covalent bond or a non-polar covalent compound would be any diatomic. All right. H2, O2, Cl2. Think about it. If an atom is pulling or in a tug of war against itself, nobody's going to win that tug of war. It's going to be completely equal sharing of electrons. Okay? So just imagine if you were like in a tug of war against your twin. The tug of war is not really going to go anywhere. It's going to be an equal sharing here. So I love this picture down here with the Cl2 because this blue area is showing you the electron cloud. So when chlorine is in a bond here or sharing with itself, you can see the electrons are equally shared between the two. That is a non-polar bond. So polar covalent bonds are when the electrons are not equally shared. So they are polar. They have an unequal sharing of electrons. So that means one atom is getting the electrons more. All right. So property-wise here, they're kind of opposite. These compounds are soluble in water, like dissolves like. Water is polar, so it will dissolve other polar substances here. And their boiling and melting points are a little bit higher, okay, than non-polar compounds, but they're still low. All right, they're covalent. Covalent have low boiling and melting points. It's just that these are a little bit higher than non-polar. All right, so an easy example here of a polar covalent bond would be O bonded to H. All right, so if you're trying to figure out an example of a polar covalent bond, usually something bonded to fluorine or something bonded to oxygen or chlorine, as long as it's not a diatomic here, those are really good examples of polar because you want somebody who's not so electronegative bonded to somebody who is electronegative. So we know fluorine and the ones closest to fluorine are the most electronegative. So if you look at this picture here, again, this gray part, this is the electron cloud. All right, so if you notice in this picture, most of the electron cloud is around the oxygen because he's winning the tug of war and the electrons are closer to him. So that's what makes this bond polar. The electrons are not shared equally. So these differences in bond type boil down to differences in electronegativity. So if you remember, the electronegativity is the ability of an atom to attract electrons toward itself. All right, so if you see two atoms in a covalent bond and their electronegativity difference is very, very low, meaning there's not much of a difference, that's when you get these non-polar covalent compounds. They're going to share and they're going to share equally because there's not a great difference between their electronegativities. They both kind of can attract the electrons toward themselves equally, so you end up with an equal sharing. Okay, you never need to memorize these numbers or memorize this table. It's more or less something you kind of think of, and it kind of makes sense here. So this is just an example. If you had S bonded to Se, and you look up the electronegativity values, the difference is 0.1. So this would be a nonpolar covalent bond. There's not much of a difference between the electronegativities. They would share equally, right? When you get a greater electronegativity difference, okay, so this middle one here, that's when you get this unequal sharing of electrons, all right? If you get the difference to be great enough that one of these atoms has a greater electronegativity, it's going to win the tug of war, and it's going to be a polar covalent bond here. And then you'll notice here, ionic is when you have such a great difference, right? Between a metal and a non-metal here, all right, if you actually do this and look at the electronegativity difference, they're usually off the charts because it makes sense. Metals don't want their electrons, non-metals want the electrons, so you would expect the electronegativity difference to be very large here. So polar is when there is a difference between the two atoms in terms of the electronegativity difference, but not so great that it's going to be an ionic bond here. So just so we can look at an example here, we're going to start with HCl. All right, if you looked up the electronegativity values of these two substances, H has an electronegativity of 2.1, chlorine has an electronegativity of 3.0. When you do this subtracting, all right, the difference is 0.9, and on that chart, it does make this a polar bond. It makes sense. Hydrogen's not very electronegative. Chlorine is very close to fluorine, so he is very electronegative. He's going to win the tug of war and pull the electrons toward itself. All right, so chlorine is going to hog the electrons, which would give him a slightly negative charge. It makes sense. If the electrons are closer to chlorine, all right, he's going to have a slight negative charge. All right, and then the hydrogen doesn't win the tug of war, so he doesn't have the electrons toward himself as much, so he's going to be what we call slightly positive. Again, if you look at this electron cloud diagram here, more of the cloud is around the chlorine because he's winning the tug of war. So let's talk a little bit about these partial charges, okay? They're not real charges. These are not like the +1 or -1 that you'd see in ionic bonding. These are just slight regions of charge due to one of these elements winning the tug of war a little bit more. So we use a delta to denote that, and it could look like this. If you see that, that just means this means slightly positive, this means slightly negative. You need to realize that it's not a real charge. So if we look at that example we just did, HCl, we said chlorine wins the tug of war more, so he's going to be slightly negative, and then the hydrogen is not winning that tug of war, so he would have the electrons less and be slightly positive. Another way to write it is like this, okay? Basically, you would put the positive sign over the one that's positive, and then you draw an arrow toward the one that is winning the tug of war. So it kind of points at the one who is grabbing the electrons a little bit more. All right, so just having a polar bond doesn't make a molecule itself overall be polar. All right, in order to have an entire molecule be polar, all right, it has to have a polar bond and the right shape. All right, it has to be a dipole. Dipole just means it has two poles, essentially a positive region and a minus region. Okay, so we're going to look at this idea of what it takes to be a polar molecule a little bit more. So, as we said here, in order for a molecule, the entire molecule to be polar, okay, it must meet two requirements here, okay? So the first requirement here is you need at least one polar bond. As long as the molecule has a polar bond in it, all right, it could potentially be polar here as a molecule. So having a polar bond, okay, could make the overall molecule polar. But the other thing you need is an asymmetrical shape, all right, or asymmetrical atoms here. And we try to make this as simple as possible here, but the idea is look for lone pairs on the center atom, because a lot of times lone pairs on the center atom lead to these asymmetrical shapes. All right, so usually what I say here is I'm not trying to trick you. If I give you a molecule and say, is it polar? Okay, as long as it's not an ionic compound or as long as I didn't give you a diatomic, you're going to assume, okay, it has a polar bond. Mr. Little's not trying to trick you. He's not going to make you look up the values. So the the thing you're looking for here is if you're trying to decide if something is polar or not, you're looking for an asymmetrical shape, typically lone pairs on the center atom. You want a shape that is not symmetric, all right? So you're going to have to draw the dot structure, look at the center atom, see if you see those lone pairs, see if it has an asymmetric shape, and that would tell you if it's polar or nonpolar. If it has an asymmetric shape, the molecule itself is polar. If it doesn't, it's going to be nonpolar. Okay, so just having polar bonds is not enough to make the entire molecule polar. All right, as we're going to see here, we're going to look at these examples between water and carbon dioxide. They both have a center atom with two things attached to that atom, but one of them is going to be polar and one of them is going to be not polar based on the shape here. So let's look at water first, okay? Water has two polar bonds present in it. The O, single H are both polar bonds. If you looked up the value, they would fall in that polar region, okay? The oxygen is more electronegative. It's closer to fluorine, so he's going to pull away those electrons from the hydrogen and win the tug of war more, okay? But that's not enough to make the overall molecule water polar. Okay, water itself has an asymmetrical shape here. All right, if you draw the dot structure of water, okay, remember, assume, hey, look, Mr. Little didn't give me an ionic compound. It's not a diatomic here. We are assuming it has polar bonds. So the other thing I'm looking for is, are there lone pairs on the center atom? Does this have an asymmetric shape? All right, if you look at the dot structure here, notice the center atom is the oxygen, and there are lone pairs on it. Okay, so that should be a dead giveaway here that this molecule is going to be polar. The shape is asymmetric because it bends down. Okay, so if you look here at the picture, right, this is showing you the regions. Notice the oxygen is more blue because it's indicating that it's more negative, and the hydrogens are more green because they're indicating that they're more positive. Okay, so in order to be polar, you have to have polar bonds, check that off the list, and the right shape. Draw a dot structure, look for lone pairs or an asymmetric shape for the center, and you'll know if it's polar or not. So notice the difference here with CO2. CO2 has two polar bonds as well. Carbon single bond to the oxygen. If you look up the values here on for the electronegativity, they would fall in that polar region. Okay, the oxygen is more electronegative. It's pulling the electrons closer to itself. However, when you do the dot structure, it has a symmetrical shape. It's linear. Okay, so if you look at the center atom, the carbon would have no lone pairs on the center. All right, it forms a line essentially. So because of that, this molecule itself is non-polar. It has polar bonds, but it doesn't have the right shape in order to make it polar. If it has a symmetric shape, it's going to be non-polar as a molecule. So the entire molecule for CO2 is non-polar. So I just want to do a quick example here so you could see how to apply this. Assume here I gave you this question. I said, okay, well, determine if the molecule CH4 is polar or nonpolar. Just like shape and hybridization, if you're trying to figure out polarity, you need to draw the dot structure, okay? Draw the dot structure and that'll tell you if it's polar or nonpolar. That's why you need to be really good with these dot structures. So, all right, if it's CH4, go through the steps, do the dot structure. There's 4 valence electrons for each carbon times 1 carbon, plus there's 1 valence electron for a hydrogen times 4 hydrogen. All right, that gives me a grand total here of 8 electrons that must be in my picture. All right, so then the rules say carbons or nitrogens in the center. I got a carbon, so it's going in the center. Whatever's left goes around him. So there's 4 hydrogens left. All right, whoever you put next to the center needs to share at least a pair with the center. Remember, that's the definition of covalent. All right, and then you need to make everybody happy. Okay, so right now in the picture here, each hydrogen has 2, so hydrogen is happy, and the carbon has 8, so carbon is happy as well. So you have to make everybody happy. Remember, if you're wrong, you'll figure it out. And then now you count. Well, when I count up my electrons, I did hit that magic number of 8, so I'm good. All right, this is the dot structure of CH4. Now, the last part here is to determine if it's polar or nonpolar. All right, remember, there are 2 requirements here to be polar. All right, we said in order to be polar, the first thing you need is polar bonds. Okay, so as long as this is not ionic, all right, it's not a metal and a non-metal, it's not a diatomic, you're assuming it has polar bonds. Mr. Little is not trying to trick you, okay? So the second thing you need, okay, is that asymmetric shape here, all right? So we're looking for, most of the time, you're looking for lone pairs on that center atom. If you see lone pairs on the center atom, you can say polar, all right? So when I look at the center atom here, this carbon, all those electrons are shared with the hydrogens. So there are no lone pairs on the center atom, all right? So if there are no lone pairs, you say nonpolar. All right, I try to make it as simple as possible here for you. All right, draw the dot structure, look for lone pairs on the center atom, look for that asymmetric shape, and that'll tell you if it's polar or nonpolar. If you see lone pairs on the center atom, you see that asymmetric shape, you say polar. If you see no lone pairs on the center atom when you do the dot structure, you say nonpolar. So let's try another example here. Let's do this for PF3. Again, you're more than welcome to pause the video, try this on your own, all right? But we're trying to see if PF3 is polar or nonpolar. So just like shape and hybridization, if you're asked about shape, hybridization, or polar or nonpolar, draw the dot structure, okay? So PF3 here. First element I see is phosphorus. Phosphorus has 5 valence electrons, times there's 1 phosphorus, plus each fluorine has 7 valence electrons times 3, right? So that's going to be 21 plus 5 is going to be 26 total electrons in my picture, all right? Carbons or nitrogens in the center. There are none, so I put the element there's less of in the center. So there's just 1 phosphorus, so phosphorus is going to go in the center. Whatever's left goes around him. So I got 3 fluorines. All right, I'll put them as evenly as I can around the phosphorus. Whoever you put next to the center has to share at least a pair with the center. Okay, and then make every element happy. So each fluorine is going to need 6 more, so that each fluorine has that magic number of 8. And then phosphorus here only has 6, so he's going to need an extra 2 as well. Remember, the rule says make everybody happy. If you're wrong, you'll figure it out in a second when you total this up. All right, so now when you go back through and count up here, make sure you're counting carefully, you'll see you hit 26 electrons. Okay, so everybody's happy and you hit your magic number here of 26, so that means this is the dot structure of PF3. All right, so the last step here to determine if this is polar or nonpolar, okay, is, all right, do you have polar bonds? Remember, assume, I'm not trying to trick you, as long as it's not a ionic or it's not a diatomic, it has polar bonds. So we look at the center, all right? Are there lone pairs on the center atom? And in this case, the phosphorus has a lone pair of electrons there. So you can say here, this is going to be polar, okay? Draw it, look at the dot structure. If you see lone pairs on the center atom, you roll polar because it's going to have an asymmetric shape here. This shape is going to be trigonal pyramidal, all right, and that's going to be an asymmetric shape. So again, to do polarity, draw the dot structure, look at the center atom. If you don't see lone pairs, symmetric shape, you say nonpolar. If you see lone pairs of electrons on the center atom, all right, an asymmetric shape, you say polar. I'm now going to walk you through something here called intermolecular attractions. These are also known as intermolecular forces, so sometimes we just call them IMFs, okay, for short, intermolecular forces here. And these are just the attractions between molecules that allow the molecules themselves to stick together. These are not the bonds between atoms. These are the attractions between the molecules themselves. Okay, so these are not true bonds. If you look here in this picture, when hydrogen forms a covalent bond with chlorine, that's a real bond. That's a shared pair of electrons, okay? But when 2 molecules here of HCl form an attraction between them, that's an intermolecular attraction or an intermolecular force. Okay, so that's what we're talking about here. We're talking about these attractions between molecules. They are way weaker than an ionic or covalent bond, so that's why we use a dashed line to indicate them. And basically, this is what allows these solid and liquid covalent compounds to actually form. Otherwise, they would all just be gases. They would be so far apart that they would just be gases. So these attractions that take place allow these solid and liquid compounds to be present. And this actually does contribute to the properties here of the substances. The reason why water acts the way it does is because of the intermolecular attractions that are present. So these are not real bonds. These are what keep the molecules attracted to each other. The first type of IMF we're going to look at here is called London dispersion forces. Okay, sometimes this is just abbreviated as LDFs for short. All right, so if you see LDFs, that's just talking about these London dispersion forces. Okay, and this is all due to this random movement of electrons in nonpolar molecules. Okay, so you would expect to see this be the strongest or the most common form of intermolecular attraction in non-polar molecules. Okay, so literally what happens here, all right, let's just look at this example. If we have I2, iodine, all right, remember, this is a non-polar molecule. It's a diatomic. It's pulling against itself, all right? You would not expect there to be this unequal sharing of electrons, okay? Nobody's going to win the tug of war if you're pulling against yourself. However, just due to random chance, all right, when, random collisions here of these molecules, okay, what happens is some electrons get to one side of the atom here more than the other. All right, so just due to random chance, the electrons shift more to one side. So that causes this iodine right here to become slightly negative. We know this doesn't happen. Usually it's an equal sharing of electrons, okay? But because of these random collisions, random movement of electrons, one of these iodines gets more of the electrons around itself and becomes slightly negative. Well, this triggers kind of this response here in a neighboring molecule. So in the iodine that's next to this, it feels that, okay? So it feels this slightly negative charge. So the electrons here kind of move more toward the other side. And then this iodine becomes slightly positive, okay? It kind of senses that there's a negative charge over here, so the electrons run away, all right? Well, now you have a slight negative next to a slight positive here, so opposites attract. They form this weak attraction here between the two atoms, okay? But the idea here is that this is really, really weak because just as quick as this forms, okay, it's going to disappear because remember, this happened due to random chance. These electrons are going to shift back to being normal. It's going to go back to just being nonpolar, which would then cause these electrons to go back, and it would go back to being nonpolar, and this disappears. Okay, but the problem is this is happening kind of all over the place. These random movement of electrons randomly shifting to one side here, and that causes these weak London dispersion forces to form and then disappear. But then they form and they disappear. So these are the weakest because they're not always going to be present. The next type of IMF is called dipole-dipole interactions, okay? These are going to happen in polar molecules, okay? So think about it. Polar molecules always have that slight region of charge, okay? Part of a molecule is always slightly positive, part of it is always slightly negative, okay? So these are going to be a little bit stronger because they're not going to just form and disappear like you saw in London dispersion forces. London dispersion forces happened in nonpolar molecules in which the region of charge just shifted randomly for a brief second and then disappeared. Here, the regions of charge are always present because that's what the definition of polar is. So if you look here at this example of HCl, if you have a molecule of HCl, the chlorine is always going to be slightly negative and the hydrogen is always going to be slightly positive. So when it comes nearby another molecule of HCl, all right, when you get the slightly negative chlorine near a slightly positive hydrogen in another neighboring molecule here, they form this weak attraction, and we call that a dipole-dipole interaction. It is still just an attraction, so it's weak, but it's going to be stronger than a London dispersion force because it's not going to disappear, okay? In polar molecules here, all right, these slightly positive, slightly negative, always are there. So this kind of dipole-dipole interaction forms and then it doesn't disappear. Okay, so that's why it's a little bit stronger here than the LDFs. All right, so you need to remember here that LDFs happen in non-polar molecules as the main form. Dipole-dipole interactions are going to be the main or the stronger form in polar molecules. And the third type of IMF here is hydrogen bonding. The name is a little misleading. It's not a real bond. It's just one of these attractions, okay? It is literally just a stronger form of a dipole-dipole interaction, okay? It forms anytime you have hydrogen bonded to one of these three elements, fluorine, oxygen, or nitrogen, okay? Basically, hydrogen, which isn't electronegative that much, is bonded to one of these three elements that are very electronegative. All right, so the difference between the two is much greater. All right, so this leads to stronger dipole-dipole interactions here. So hydrogen bonding is just a specialized form of dipole-dipole interaction that's a little bit stronger. Okay, so this takes place in water. All right, water has slightly negative oxygen, and whenever that slightly negative oxygen comes in contact with a slightly positive hydrogen on a neighboring molecule, they form this hydrogen bond. Again, it's not a real bond, all right? You only see these happening if you have hydrogen bonded to F, O, or N. Just having hydrogen in a molecule doesn't mean hydrogen bonds are going to form, all right? So you still need hydrogen to be bonded to one of these three elements in order for this to take place. So I just wanted you to see here a visual here of these dipole-dipole interactions. So remember, a dipole-dipole interaction would happen in polar molecules, molecules that always have these slightly positive, slightly negative regions. So anytime you get a slightly negative in one molecule near a slightly positive in a neighboring molecule, they form this weak attraction. But remember, it would be happening all over the place. If this was a beaker of HCl, this would be happening between all the different molecules here of the HCl in the entire beaker. And this does contribute to properties here, because if you wanted to, separate these molecules, if you wanted to say maybe get the substance to boil, you have to go through and break all these IMFs here that are present. Okay, so this would be dipole-dipole. It would happen in polar molecules. It's a little bit stronger than LDFs, but still ultimately it's just an attraction, so it's not as strong as a real bond. The bond would be between the atoms themselves. These are just attractions. So again, just showing you these dipole-dipole interactions here. So whenever you have a polar molecule with slight positive, slight negative regions, anytime the slightly negative comes nearby to a neighboring molecule with the slightly positive, they form this weak attraction. Okay, the opposites are attracting, but again, they are not real bonds. They are just attractions here between the molecules. So this is just an example of hydrogen bonding that occurs in water. Remember, this is a specialized form of a dipole-dipole. It only happens when hydrogen is bonded to one of those three elements, fluorine, oxygen, or nitrogen. So in this case, hydrogen is bonded to oxygen. The oxygen is going to be slightly negative, always in water. He's hogging the electrons more. Each hydrogen in water is slightly positive. Okay, so anytime you get this slightly negative oxygen in a water molecule nearby, to a neighboring hydrogen in a different water molecule that's slightly positive, opposites attract, so they form this weak attraction there. That's a hydrogen bond. Again, it's not a real bond, it's just an attraction. So just want you to see here, if this was an entire beaker of water, you would be seeing these hydrogen bonds taking place between all these different molecules of water all over the place. Okay, so anytime you get a slightly negative oxygen nearby a slightly positive hydrogen in a neighboring molecule, they will form this attraction here, or this hydrogen bond. Same thing, this is just showing you how the slightly negative oxygen coming in contact with a slightly positive hydrogen in a neighboring water molecule would form these hydrogen bonds. When we were going through polarity, we talked about how polar substances will dissolve in water because of that old saying, like dissolves like. So this is just a little comic here that's pretty funny. The polar bear says, help, help, I'm dissolving. The other bear there says, but bears are insoluble. And the polar bear says, that's easy for you to say, you're not polar. Okay, so the polar bear is saying essentially he's going to dissolve because like dissolves like. If water is polar, you would expect it to dissolve polar substances. You can laugh now. The last thing I want to point out here is that because of these differing intermolecular attractions that can occur in these covalent substances, The covalent compounds have a wide variety of physical properties. If you remember when we did properties of covalent compounds, we said, they're not typically going to be solids, but some can. You have sugar existing. They're not typically going to dissolve in water, but some can, like sugar. All right, and it's all because of these different or this wide variety here of intermolecular attractions that exist. There's something special here called network solids. These are these very, very stable covalent compounds. All right. It's a stable structure in which every single atom is covalently bonded to every other atom in the structure. And it leads to these solids, which you might think they were ionic. All right. They have very high melting points, 1,000 degrees Celsius or higher. So, for example, if you wanted to melt one of these compounds, you would have to break every single covalent bond, which would take a lot of energy. That's why the melting points are so high. So, a good example of this would be a diamond. All right. If you look here at the structure, these atoms here are all carbon atoms, and every single carbon atom is covalently bonded to every other carbon atom. Okay, so this creates this network solid, which is this really stable structure that you might think is an ionic compound, but it's not. It's actually covalent. Okay, it's just that every other atom is covalently bonded to every other carbon atom, so it leads to this really stable structure that needs a lot of energy in order to break all those bonds. So you can expect a wide variety of properties here with covalent compounds.